everybody. Can you hear me? So first of all, sorry for the technical kind of problems last time. I hope this time everything will go way smoother, and we'll all will be happy to kind of use this nice networking features of Hermit. So just a few things. So if you are looking for information about upcoming colloquia or past colloquia, I mean, you can find them on IGAFIT webpage. And importantly, I mean, we plan to have recordings of all the talks, and you'll be able to find them in past IGAFIT colloquia page. And in particular, Vera's talk is already there, so you can check what you have been missing last time. And I hope things will go more smoothly starting from this meeting. So in general, to ask question, you should use this questions tab, and please submit your questions. So if I mean, the speaker will try to answer the questions during the talk, but if this will not be the case, then we will have a question session after the talk. So I will bring everybody who has submitted a question to the stage, and you will be able to ask your question and discuss with the speaker. So please do it. If anything comes to your mind during the talk, please submit a question. In general, so if you have any comments to how things work or have any suggestions, then please do contact anybody from the committee, and then please let us know so that like we all can enjoy this meeting, and I hope it will play a kind of a role of seeing each other and keeping connected, as it seems that in Europe kind of the situation is getting worse with the pandemic situation. So I hope this will be a way to kind of communicate and see new and cool results. Okay, so this talk will be given by Thatchaphol Saranurak. And it will be on kind of recent advances on expanded decomposition. And Thatchaphol decided to give a slightly bigger view on the problem than suggested by the original title and abstract. And I think I really like this approach. So we'll see like all cool applications of this new technique. So please go ahead and
just to make sure everyone can hear me, right? Okay, cool. So now I will start. All right, so this talk, I will talk about application of expanders to graph algorithms. Originally, I will talk about this result only, but I think it might be more exciting for you to see the whole picture more. So let's start. So in the talk, we always talk about graph. So throughout the talk, n is the number of vertices, m number of edges, and I use O tilde to hide polylog, O hat to hide subpolynomial factor, and actually I often hide it in the table when there are many numbers. All right, so expander, we have seen it many times. Because it appears in many contexts like random graph or hypercube, or even the graph defined by a finite field. So it's just mean that the graph is robustly connected. And more formally, we say that the graph is a phi expander if for any cut in the graph S, okay, this cut, the cut size over the volume, this ratio is at least phi. In other words, like the total weight of edges crossing the cut over basically the total weight of edges incident to the cut. This ratio is at least phi, right? So if you look at any set here, it kind of expand a lot compared to the volume where you count the edges inside as well. All right, so expanders are great. They are used to construct a lot of very strong objects like error correcting code and like other things. And you can see this fantastic talk by Avi, which talk about a lot of application of very strong expander. And moreover, expander also is very algorithmic friendly. It usually admits faster and simpler algorithm for many graph problem. But then not all graphs are expander, right? So the question is, the general question is that, can we exploit the greatness of expander even in the non-expander graph? That's the question. And yeah, the answer is yes. And how to do that is to use expander decomposition. So let's see what it is. So expander decomposition is the problem where you are given a graph and a parameter phi, and you need to output a partition of vertices such that in each part each part induce a phi expander. And not only that, the number of edges crossing each part, that should be small. So it should be around just 5 fraction of edges that are crossing. So if you choose phi to be small enough, this would be like less than half or anything that you like. You just choose parameter phi as small as you want. So it's known that this expander decomposition exists, and it's already a nice fact to know, right? That for any graph is really just a bunch of disjoint expanders plus a small fraction of edges. So that's good to know. And there are some polynomial time algorithm, we know how to compute it. But just very recently, we show that this decomposition actually can be computed deterministically in almost linear time. It's not how to do it randomized, but we just recently showed that now it can be done deterministically. All right, so you can find this thing very fast. And let's look at some example. So this is just some example of expanded decomposition. So you can see that it gives some natural graph clustering to you. In the extreme case, when the graph is just a path, what it will give you is this thing, where you just divide the path into subpath, and each subpath have length 1/5. So kind of natural clustering again. So it's the kind of natural graph clustering. Let's have a look. What if we used expanded decomposition on the graph repeatedly? So what do I mean by that? So given a graph, what if we just apply expanded decomposition when phi is small enough? Then what you get is that the number of intercluster edges is less than half. And each part will be still quite good expander. So this is still quite high. And if you just take the graph induced by the red edges, which is less than half of total number of edges, look at this graph induced by the red edges and do expanded decomposition again. Then you get another expanded decomposition, and now the green edges is less than 1/4 of the whole number of edges. And now you can repeat. You get the idea, right? You can repeat only log n times. And what do we get now? We can see that given this graph, you can get G1 up to G log n, where each of the graph is now a disjoint, disjoint of expander, disjoint union of expander, and they partition the whole graph. So this is just another view which says that every graph, you can view it as really a disjoint union. No, not disjoint union, but a union of expanders. And each vertex, although it's not disjoint union, but each vertex can appear in at most log n expander, because each vertex can appear at most one in each GI. So this view will be useful for us as well. So this is two view of how any graph is close to expander. One is just expanded decomposition, another one is repeated expanded decomposition. All right. So now in this talk, I want to tell you like an overview how are these useful? How do we use it, right? And there are actually many things we can use it for. So let's start with the first thing. It's about the randomization of static algorithms. So if you look at this problem, there are classical problems like map flow, shortest path, Laplacian solvers, and so on. So in all of these problems, people have tried to get a fast algorithm, right? And there have been like it had been shown with like some deterministic algorithm which is quite fast, but not so fast yet. And then people successfully improve the running time to near linear even for some problem. But now these algorithms are randomized and Monte Carlo, so they can err. Now it turns out that with deterministic expanded decomposition, we can use it to de-randomize all of this. So without sacrificing the running time, we can make it deterministic, all of this. So I want to tell you a bit how do we do it. So it turns out that the starting point is how to compute the thing called cut specifiers. So in this problem, you are given a graph, and then you want to output the cut specifier h of g, and which is a graph such that it has only few edges, like it has only linear in n, almost linear in n number of edges, but the edges can be weighted. So that's what it means by sparse. And moreover, for each cut in the graph, each cut S, the cut size should be approximated by h. So the cut size in h and in g should be within factor alpha. So that's why it's called cut specifier. So we know, like a long time ago, Benshaw and Karger shows that we can compute this in nonlinear time, and with very good approximation, but it's randomized. Then one know how to do it deterministically as well, but the time is slow. So we know what we show is that, okay, we can make it fast if we sacrifice the approximation ratio. By the way, it's still open if you can do the best of both worlds, like a fast and good approximation, and we want deterministic as well. So this is a great open problem, I think. But let's see how do we do this. It will be simple, actually. So the idea is this. So recall that every graph is just a union of expanders by repeated expanded decomposition. So once we just compute this thing, we have another fact that we will use. That is, it turns out that for any expander, it's very easy to specify. That is, we can get 1/5 cut specifier of G in linear time. And to do that, actually, you can just take H to be a graph, which is a expander. Even phi expander would be fine. That And but a graph which is a very good expander with linear number of edges exists. And moreover, you can also choose the weighted degree of H to be close to the degree of G. So it is easy to prove that if you have this graph H, then H will be 1/5 cut specifier of G. It's very easy to prove, and I will not prove it for you. It's really just comparing using the definition and so on. And you can construct H in nonlinear time, basically by combining non-explicit expander together and scale the weight appropriately. But then once you have that, you can specify expander very easily. And you know that every graph is just a union of expander. Now it's kind of, is H the subgraph of G? H need not be a subgraph of G in this case. Yeah. All right. So now with these two things, we know what to do. So given any graph G, you just look at each expander in the repeated expander decomposition and then specify it using fact 1. All right. And now, so now what you do is that once you specify each expander, look at the specified expander and union all of them, and you get the graph H. And now we will use this fact, which is again easy to prove. That is, if a graph G can be partitioned into Gi, and each Hi is a cut specifier of Gi, then H, which is the union of all Hi, will be also the cut specifier of G. And by this, we can conclude that, all right, now H, the union of every specified expander, will be a cut specifier of a G. And the time is nonlinear. So what I just like a sketch for you is that, okay, from expander decomposition, you can get the cut specifier with kind of bad approximation. The same proof would go through for spectral specifier, actually. There is a question, why H is sparse, why the degree of H is close to U? This is because H is weighted, and we just choose weighted degree to be close to G. So it has few edges, but the weighted degree is close to the degree of G. All right. All right. So now we get cut specifier. And it turns out that once you have cut specifier, you can use non-reduction to get oblivious routing, map flow, and so on. Like there are non-reduction which are deterministic with some tweaks, by the way, but it can be done almost immediately. And once you have that, you get everything. So that is that's how we de-randomize all of this. Sorry. Now, so that's part 1. Now let's go to the part 2. It's about dynamic algorithms. So as a running example, I will tell you about dynamic connectivity. In this problem, you want to have a data structure on a graph, and it need to maintain whether the graph is still connected or not. So here, the graph is connected, so it must return yes. But then there is a stream of updates, edge update. And here you delete an edge, 1, 3. The graph is still connected, so it says yes. The next update comes. Now you need to say no because they are not connected. There can be some insertion. Once this edge is inserted, now you need to say yes, and so on. This goes on. All right. And if you want to do everything from scratch, just spend linear time, but obviously that's not good for us. It's too slow. But Frederickson and Epstein et al. Already show us how to do it in root n time since the 90s. Then people kind of get stuck, although there is a lot of success in related setting, but we now talk about worst case update time. And people keep asking the same question. Actually, this is really like a major problem, that can you do deterministic algorithm faster than root n? It turns out that Capron-King and Mountjoy can do faster than root n, but it's not deterministic yet. But this is a breakthrough already. And then it turns out that just recently, from the same paper, we can do it. We can get n to the little one time deterministic. And the key idea behind all of this development is expanded decomposition in the dynamic setting. And it's actually not just connectivity that we can use dynamic expanded decomposition for. By using, like, extending the same framework in a very non-obvious way, but it's kind of use the same tool. We can use it for breaking a lot of barriers in other classical problems like MST, map flow, reachability, and so on. So let me tell you what is dynamic expanded decomposition. So this is expanded decomposition. We have seen it. For dynamic one, it's the same thing, except that we want to maintain this same structure under edge updates. So now we want to maintain this partition of vertices. The number of parts can change, k can change, and I will focus only in the case when the expander is quite good, so phi is quite high. All right. And we also want the number of edges crossing to be 1 over n to the little one. Yeah. So that's the dynamic expanded decomposition, and we show that we can maintain this structure actually with only subpolynomial worst case update time, as long as the number of update is not too many. It's not it's still kind of sublinear, and this can be done deterministically to maintain this structure. So in the remaining part of this second part, I will first tell you how to make a static expanded decomposition dynamic. And then I tell you how to use it for dynamic connectivity. Right. For the first part, the main tool is the thing called expanded pruning. And this is the tool which is used by actually all dynamic algorithms that exploit expander. It really enable us to use expander in dynamic setting. So it's a nice tool to know. But the first intuition I want you to see is that expanders are robust under updates. That is, if the graph is not expander, right? You might have sparse cut here, and if you just delete few edges here, then you get a very too big connected component. This is a big change that we don't like. On the other hand, if the graph is an expander and you just delete few edges, you delete edges here, you know that there must be a lot of edges crossing this cut because the cut is expanding and this cut is balanced. So you cannot really disconnect it. Or even if you delete many edges around some small part, you can, at most, as long as there are few edges here, you can only disconnect very small part of the graph. So that is small change, and we like it in the dynamic setting. So now expanded pruning is something that use exploit this intuition, and it works even in the online setting. That is, if you start from expander, and then suppose that there is one update to the graph, the algorithm will maintain a vertex set P. It will return a set P, right? With this promise, that is, the complement of P will remain an expander. So you have some update, just one update. There can be very small problematic part in the graph. You remove that part. The set P will be around that. And if you say that if you remove that set P, the complement is still an expander. Everything is still good. And so on. Then the next update comes, you update the algorithm, update the set P, and the complement remain an expander, and so on. All right. So that is what it does. And the nice thing about the guarantee here is that you can guarantee that the set P, the problematic part, can grow only very, very slowly. So the set P at time I, the volume of the set is at most I times something small. And the time to update the set is also small. So that is what expanded pruning is. Basically, for each update, the problematic set grows very, very slowly. It causes you small problem, and the remaining part is still expander with all the great properties that you want from it. Okay, and note that you really exploit expander, right? Because if there is a sparse cut here, just after deleting two edges, in order to make the P like a complement of P connect, that P must be this big immediately. So it can grow slowly only if the graph is an expander. And now how to dynamize expanded decomposition. Given a static expanded decomposition, what you do is just run expanded pruning on each expander. So you have a graph, then run expanded pruning on each expander. When there are some updates coming to you, you keep pruning it. And what you have is that the remaining part in each expander, this remaining part is still a good expander. And moreover, the part that you prune out, the volume will be quite small because of the guarantee of expanded pruning, as long as the number of updates is not too big. So you can basically treat all of this part as the red edges, as the intercluster edges. And to get altogether, the red edges is still small. And you have the blue part as an expander. So this already gives us dynamic expanded decomposition. We get this structure now. All right. So now we get dynamic expanded decomposition. Let's see a bit how to use it for dynamic connectivity. So one simple idea is to use something called hierarchy of expander. So if you have a graph G, you do expanded decomposition, you get expander, and there are few edges, intercluster edges. What if we contract each expander into a vertex? So you contract each expander, and the red edges is preserved. So this graph will be smaller, right? Because the number of red edges is small. And you can repeat this to get the expanded decomposition, and now contract each red cluster, and so on, until there is no edges to contract. So once you have this, observe that there actually will be even less than log n levels, because the number of edges actually is reduced by subpolynomial factor, not just a constant factor. So once we have this, what do we get? Now it's kind of trivial how to answer if the graph is connected or not, because in the last level you have one vertex if and only if the graph is connected. So now you answer yes if you start with two components. The last level you have two vertices at least. Okay. So now the idea is you just maintain this dynamic expanded decomposition on each level of the hierarchy. All right. So once you maintain this dynamic expanded decomposition, then you just get this hierarchy dynamically. And that's how you can answer connectivity. By the way, I hide something under the rug. That is actually, in order to make this idea work formally, you need some stronger expanded decomposition from this paper. And because otherwise the update would propagate too quickly from the update from the bottommost layer will propagate too quickly to the top layer. So it wouldn't work yet, but this is the idea. And then, yeah, so once you have this expanded decomposition, dynamic expanded decomposition, you can extend it in many ways. And that is how we use it for many other problems. There should be more, right? And so I just want to kind of give you some very philosophical explanation why all of this work. First of all, expander are robust. You know from expander pruning that it changes only slowly for each update. So it's good for the dynamic setting. And expander are algorithmic friendly. In our case, expander is trivially connected, and that leads us to dynamic connectivity. But it's not just connected. Expander admit many more, like a fast dynamic algorithm. It's easy to specify and so on. And that leads us to other results. And expanded decomposition basically find you where are the expander. So that's how. That's why everything works out. Okay, so that is the second part. Now, third part. Speed up iterative methods. And this is actually basically, I view it as an application of dynamic expanded decomposition to the static setting, not just dynamic setting now. Now it gives us the power even in the static setting. And the first application that I will tell you is just a classical problem, maximum bipartite matching. So in this graph, you are given bipartite graph. In this problem, you are given bipartite graph, and you want to find maximum number of disjoint edges, like here. And for this problem, people know quite fast algorithms since the 70s already, and like half century ago. But no algorithm was nonlinear before this work. So basically, we successfully show that now we get nonlinear time algorithm as long as the graph is not too sparse, as long as the number of edges is at least n to the 1.5. And this is not just bipartite matching, right? Like many more problems, mean cause be perfect matching, transshipment, and so on. So I want to tell you in high level, how do we do this? The algorithm is based on interior point method. So let me tell you a bit about the previous interior point method by Lee and Sidford for solving this kind of problem. So there will be square root n iteration in the in the algorithm. And in each iteration, essentially, you just need to compute several electrical flow. And each electrical flow just takes linear time in M. And that is how you get this kind of running time. It's a very high level view, but that is kind of capture what it is. Now, this work is also based on its interpolation method. And the number of iterations is still square root n, but the method is more robust in the sense that there is a question, is this exact or approximate? This is exact. This problem, this is exact. Yeah. Everything here is exact. Okay. And now, okay. So now there is, okay. In each iteration is more robust in the sense that you don't need to compute the whole electrical flow. What you really need is instead, you just need to list all edges that have large electrical flow in it. All right. So that is the thing that we want to solve in each iteration, and something more actually, but this is kind of capture what we need to do. And it turns out that we can spend, if the problem is a bit simpler, now we just want to list all edges with large flow. You can do it in linear in n time. And that is how we get this enter 1.5 here. And how to do this? It turns out that the key ingredient is two things. First, we can observe that you can actually solve this problem fast in expander. And next, in order to reduce a problem to expander, you can use dynamic expanded decomposition. And you need to be dynamic because in each iteration, the weight of the graph change by a bit. So that's why you need dynamic expanded decomposition. So that's extremely high level, but I think I have to say, that's all I have to say in this talk because I don't have enough time. The next thing is the approximate map flow. Now this is approximate. We can use it. We can get it using dynamic shortest path. And inside dynamic shortest path, it again use expanded decomposition. How to do that? I want to spend like a few minutes on this just because it's so nice. To do that is to use multiplicative weight update framework. And if you haven't seen it before, I would love to tell you about that because it's basically like a simplest framework for computing map flow. You will never forget it. So it's really a simplest algorithm, I know, because it says this. You just initialize all the edge weight with something tiny. And then you just look at the distance between S and T. As long as the distance is less than 1, you find the shortest path in the current graph and add that path into your flow. Then increase the weight of edges along the path by 1 plus epsilon factor. Now the distance might increase by a bit. Then you keep finding another shortest path, add it into your flow, keep and increase the weight and repeat like this. Once the distance is greater than 1, now F is already an approximate map flow. So it's very simple after some scaling, by the way. So this is like conceptually so simple. And you can see that from this algorithm, dynamic shortest path algorithm is really fit into this framework. So instead of finding shortest path in each iteration, you use dynamic data structure to spend sublinear time per iteration, right? To get the shortest path. And that is how we speed up map flow. By the way, previous dynamic shortest path algorithm exists, but they do not work in this setting because they assume that the adversary is oblivious to the answer of the algorithm. The adversary that generates the update is oblivious. And this is opposite of this, right? Because the updates here depend directly on the answer of the algorithm. So that's why it doesn't work. But now expanded decomposition allows it to work against adaptive adversary, and that's why everything works. All right, so now we switch gear a bit to distributed algorithm. I will be quick now. So I need to start with defining the model, which is congest. In this model, you have distributed network. Each node is, you think of it as a computer that can do local communication. So in each round, each node can send a message to its neighbor. And the message should be small. The size of the message should be small. And what you want to do is to compute something about underlying network and minimize the number of rounds. There is a stronger model called congested clique. It's strictly stronger in this sense. Instead of local communication, now you allow all-to-all communication. So now even 1 and 4 can talk to each other. Each node can send a message to everyone in one round. But they still want to compute something about the blue graph, right? Not the purple one. Okay. So that's the two models. And it turns out that in this classical problem, like listing all the triangle, people know type bound, which is n to the one third in congested clique, and some generalization to k-clique listing. For congest, it was slower. And that is not so surprising because the model is weaker. It's harder to find the algorithm. It turns out that you can use expanded decomposition again to match the bound to be n to the one third, and also k-clique listing. So that is nice. It means that we can kind of like locality is not really a constraint for us at all. By using expanded decomposition and routing, I will tell you what it is. What are they? You can basically kind of transfer strong result that holds in congested clique to congest with locality constraint. So we kind of, at least it is true for triangle listing and k-clique listing. We want to know whether there are more connections like this actually. But what are they? What are these tools, right? So again, in congest now it's the same problem, but in this distributed setting, which means that, okay, instead of outputting the partition in one computer, we just want each node to know I where U is in VI. And we can compute this within small number of rounds, deterministic. Repeated expanded decomposition is the same thing, but in congest. It's just like you just get the union of expanders, and you can do it in small number of rounds. The last tool I want to tell you in this talk is expanded routing. And informally, what it allows you to do is this. It allows each node U to exchange degree many messages with any set of nodes in almost one round if the graph is an expander. So note that normally you can exchange degree many message with only neighbor in one round. Now instead of neighbor, You just say any set of nodes in almost one round if the graph is an expander. So basically, it kind of allow all-to-all communication like in congested click with small overhead, right? So that is what it does. And now, given expander routing and expanded decomposition, this is the algorithm in high level for triangle listing. You could first find this union of expander using expanded decomposition repeatedly. And then on each expander, you can basically use expanded routing to kind of almost simulate the algorithm by in congested click. Use the same idea. It's not really a black box simulation, but it's kind of use the same idea to adapt it and make congested click algorithm work in congest in each expander. And the algorithm will run in n to the 1/3 rounds, because that's how much it takes in congested click as well. So in each expander, you simulate this, and then we can guarantee that if the triangle appears in this expander, then the listing algorithm on this expander will return this, will report this triangle. And if as everything is happen in parallel, then you can get it. You can get this time. So that's how you get the n to the 1/3 time. So that now I want to recap and tell you some open problem. So you have seen 4 kind of application. We de-randomize static algorithm without sacrificing running time. We get a lot of dynamic algorithms from this. Also, we can use dynamic expanded decomposition to speed up each iteration in the iterative method and get exact bipartite matching. And also kind of transfer strong result from congested click to congest. So that's 4 things. And the main 3 tools that we use is decomposition, pruning, and routing. I will kind of go very quickly over the state of the art of all of this and tell you about open problem on these 3 tools. And you will see actually that a lot of open problem is about improving n to the little 1 to polylog. It seems incremental, but this is a common barrier for many things. And I actually believe that improving this will lead to something deep. So it's a belief, I don't know, but I think it's interesting. So expanded decomposition, in the talk, I told you about this work that we can get this. Okay, by the way, now I will use epsilon for the parameter of number, for the number of the fraction of intercluster edges here to denote it by epsilon here. And in the talk, I said this work, that is epsilon is a 5 times subpolynomial factor, and the time is almost linear. It's deterministic. What we want is obviously to remove all of this into little 1 and get polylog. And it will be very nice. But actually, even in the easier problem, we don't know how to solve this. To distinct, let alone decompose the graph into a bunch of expander. You just want to check if the graph is a very good expander, or just finding if there is distinguish 2 cases. The first case is when the graph is expander, great expander. Another case is when the graph has quite sparse cut, like 1/log to the 100 sparse cut. How to do this deterministically in nonlinear time? We don't know. If randomized, we know, but deterministic, we don't know. The same kind of thing happen in distributed setting as well. We don't have polylog deterministic polylog overhead which is deterministic. But over all of this, I want this the most actually. We want very simple algorithm. This work SW is quite simple, but not that simple yet. And if we don't have simple algorithm, the whole talk is kind of not so practical. So it's really important to have this. The next thing is it should take at least like 3 minutes more, by the way. So expanded pruning, again, just to remind you, you have a sequence of update, and you want to keep pruning some small part of the expander out so that the rest is an expander. So in the talk, I told you about the first work here, that if you start with some expander, you still get an expander with like at each time the graph is still expander and the update time is sub-polynomial. You can make it better. In this work, we say that, okay, the expansion get worse by only factor of 6 at every time. At whole time, it never get worse by a factor of 6. And the update time is kind of polylog, because you think of phi as 1/polylog, but it's amortized. The question is, can you de-amortize this? If you can, there would be some application to spanner, dynamic spanners, but there should be more actually, because it's used by all algorithms. Like expanded pruning is used by all dynamic algorithms. So the last thing, routing. I told you informally what it does, but what problem really is this problem. You have a graph G, start with expander, add another graph H, unweighted graph now, another graph H with the same degree profile as in G. And what you want, you think of each edge in H as the demand to route. So what you want is that for each edge in H, you find a path for each edge UV in H, you find a path from U to V in G, such that two things hold. Like first, each path should be small length, and next, each edge in G shouldn't be used by too many paths. So small congestion. So we want to minimize both of these together. And so that's the problem. In the distributed setting, you just say you want each vertex to know all the paths with endpoint at it. But you can define this in the centralized setting as well. It's the same thing as saying that you want to embed H into G with small dilation and congestion. That's the technical way to say. So the question is, can you do this with polylog quality, congestion plus dilation, and number of rounds? If you can, then you would speed up the whole generic transformation from PRAM algorithm to congest algorithm in expanders. That would be nice. But by the way, this problem is studied in centralized setting long time ago. And we know how to get polylog quality easily using greedy shortest path. But the time is slow. The time is m squared, because you need to compute shortest path kind of m times. So that's why it's m squared. And implicitly, the work by Ghaffari here actually gives centralized algorithm as well with almost linear time and randomized. We make it deterministic together with Julia. The question is, can you get this polylog again? If you can, then that you will get an optimal algorithm for short cycle decomposition. A nice thing to note is that variant in 82 shows a long time ago that if the graph is a hypercube, then you can do it. That is, if the graph is a good, is an expander with like good structure, then you can do it. But the question is, can you do the same thing as variant did, but on arbitrary expander? That's the question. So, so I think that is everything I have to say now. Thanks a lot for listening.
Thanks, Thatchaphol, for a great talk. And I guess we had some answers, some questions, sorry. So let me try to invite people.
Oh, I think I missed a question asked by Yossi, who asked that, can you answer how many connected components are there? I think you asked about dynamic algorithm, right? And the answer is yes. You can also maintain many information about connected components.
Mm-hmm. And I think Monica asked about whether these are exact or approximate results. I think the ones you mentioned on the slide with many results.
Right. Yeah, I think she asked about bipartite matching result, and yes, it was. Oh, this is for dynamic algorithms. For which problem?
So let me try to invite Monica.
Yeah.
So if anybody has some questions, then raise your hand. Hi, Monica.
Hello, can you hear me?
Yes.
Yep.
Hey, great talk, Thatchaphol.
Thanks a lot. Thanks a lot.
My question was on the slides, like I think it was the second part of your talk where you talked about these dynamic algorithms for shortest paths and max flow and so on. My question was, were these results approximate or exact?
Good. Right. So
yeah, exactly these ones.
This, like a lot of things, is approximate. This one approximate. This one approximate. So the only exact thing is minimum spanning tree and reachability, which is it doesn't make sense to ask about. Yeah. So approximate. The one that is approximate is spanner, max flow, and shortest path.
Okay.
And by the way, max flow here is like bad approximation. Is the like enter little one approximation. So bad approximation. Yeah.
And the shortest path?
This is 1 plus epsilon.
Okay, and this is fully dynamic?
No, sorry. This is the decremental.
Ah, decremental. So basically weight increases like you need it for your algorithm then.
Exactly. This is exactly
algorithm.
Yeah, for max flow. Yeah. Mm-hmm.
Okay, super, I get it. Thank you.
Sure.
Thanks. So are there any more questions? I guess not. So I had a question as well. So I guess this expander decomposition is only for unweighted graphs. So
yeah.
So do you have any idea whether some kind of tools will carry over to weighted graphs? Like, for example, weighted flow or that kind of stuff?
Right. So actually, for example, in this work, right, it works even in the graph where it has it works even in min cost bipartite perfect matching. Mm-hmm. So you can apply expanded decomposition, which is for unweighted graph, to weighted problem. The question is how. One way to do it is that, okay, for each you just have a weighted graph and you divide it into bucket, weight bucket. So this graph have a weight between all the edges with weight between 2 to the I and 2 to the I plus 1. You put into this graph and you decompose it, and then you try to combine the result somehow. One can that's how to use the unweighted expanded decomposition for weighted problem. That's one way.
Okay, I see. Okay, thanks. So thanks for the great talk. So I will end the session and you can have networking right now.
Sure. Yeah.
Thanks again.
Thank you.